So hello everyone, my name is Shantan and I'm a PhD student here, just about to graduate, and it's a great pleasure to be attending and speaking at this wonderful event. And I'd like to take a moment to just thank the organizers for giving me the opportunity. So with that, let's start the talk. So the title is The Role of Deformability in Yielding of Two-Dimensional Squishy Glass. And what I mean by squishy glass will hopefully become clear in the course of the talk. And the other members of the team that worked on this are Pinaki, Vani and Rahul. So to start off, yielding of amorphous solids under oscillatory shear is something which has been extensively studied. Srikanth's talk has had some of this oscillatory shear applied on glassy or applied on glasses. So I'm just going to present these two examples. I'm not going to explain the plots in the interest of time. So on the left we have a jammed system, a jammed solid, and an oscillatory shear is applied, and what we have is there is a threshold strain amplitude beyond which the system yields, and on the right we have a glass upon which an oscillatory shear is added, and we see here as well there is an existence of a threshold strain amplitude beyond which the system yields. So now for both these cases, so these are point particle models, and there is no scope for for a shape change to happen to the constituent particles. So now we can ask the question, like, what would happen if the particles are allowed to change their shapes? So you can look at this experimental paper which has recently been published. So here they had a granular assembly of rubber rings which look like this, and they apply so these are very flexible rings, and they apply a oscillatory shear to the system, and here as well there is a yielding transition with a threshold strain amplitude, and the shape, we see that the shape changes, the shape of, so this is a plot of a single particle, shape change of a single particle. So we see that it changes with the shear cycle, and an interesting thing that they see is that there is this competition between the shape change of particles and particle rearrangements. So where you have more shape change, the rearrangements are sort of hindered. So here they had just a fixed flexibility for the particles, and we want to ask the question, like how does changing the flexibility of the particles affect the yielding? So in other words, how do glassy systems of rigid and flexible particles differ in their yielding behavior? So now the first thing to do there would be to consider how to incorporate shape change in particle models. So disk based or point particle models are completely determined by the particle centers, while in vertex models there is an example picture here. We see that the shapes are restricted by dimensional constraints, and also this is only applicable to confluent systems. So now instead, if we have particles modeled as polygons or ring polymers, then both confluent and non-confluent systems can be investigated. Like in this work by Borman and others, they had these polygons and they had both rough surfaces and smooth surfaces, and we can see that there are lots of different kinds of shapes, and shape change can also happen easily. And the shape change can also influence several physical factors. So here we see that as the shape factor is increased, this packing fraction is changing. So now in our model, we had 1,000 ring polymers with 20 monomers each at a finite temperature and a large density. So how large was the how large should we take the density to be? So I'm coming to that in the next slide. And we had an LJ potential between all monomers and a FNEP potential between bonded monomers, and there is a bending energy where this k theta is, we call it the angular stiffness, and this is a measure of the flexibility of the rings, and in our work this is the tuning parameter. So we did a previous work with this kind of a ring polymer model, and what we see there is that as the density is increased, we see glassy dynamics, and we see that if this angular stiffness k theta is increased, the threshold density for which the transition happens, that becomes lower. So we choose for this work we choose the density to be high enough so that the system is in the glassy state, and instead of monodisperse rings in the previous case, here we have bidisperse rings. So because if we had monodisperse rings, then at high densities and high value of k theta, or for highly rigid rings, there is crystallization. So to prevent that, we have a bidisperse system, and so for k theta equals 10, or the more flexible rings, we see more spherical shapes, and for the more rigid rings we see more spherical shapes. So now what happens when we apply uniform shear to the system? So we get this flow curves for different values of this k theta, and we also have the solid lines are the Herschel-Buckley fits, and what we find is that the system is rigid with a finite yield stress, and as we increase the flexibility, the yield stress goes down. Now if we instead have a oscillatory shear, something like this, so gamma 0 is the strain amplitude. So there, if we look at the mean square displacements for different values of gamma 0, we see that at low values the system gets stuck, and at beyond the threshold value of the strain amplitude, it is diffusive. And from there we can plot the diffusion coefficient with gamma 0, and we get this kind of a plot for different values of the k theta, and we can fit these to power laws, and from there we can estimate the threshold value of the strain amplitude. Then we can plot that with k theta, and we see that more deformability leads to a larger yield threshold. Like here we can see that as k theta decreases from 100 to 10, there is almost a 8-fold increase of the threshold strain amplitude. And if we decrease the pressure, then we see that this increase in strain amplitude is lowered. So now what happens to the shapes while all this is happening, and we quantify the shape change by sphericity. So if we plot the distributions of the sphericities for both large and small rings and rigid and flexible rings, we see that beyond the threshold value of the strain amplitude, there is significant fattening of the tails. So, in other words, there are more and more aspherical shapes, and maybe this will become more clear in this other plot, where we have delta A versus gamma 0. So, delta A is the difference in asphericity compared to the unsheared case, and here we see that initially there is a decrease in delta A. Delta A has a negative value, which means that the asphericity is decreasing actually, which we think is because of annealing. So, Shrikant has talked about this annealing under oscillatory shear, and so after some time the delta I increases again, and we see that beyond the threshold values the increase is quite sharp. So, now we can compare the shape change and the non-affine motion of the particles over an interval of half cycle, so at 0 strain. So, here we have this scatter plot. The y-axis is dA, which is the difference in asphericity, and the x-axis is dy, the y displacement. And we have both small rings and large rings, and more flexible and more rigid rings. The green scatter is for below the threshold strain amplitude, and the red scatter is beyond the threshold strain amplitude. And this dA kind of quantifies the shape change, and dy gives the non-affine motion, since the shear is in the x direction. So, dy is the non-affine motion, and on the right we have the individual distributions of dA and dy. So, if we look at both of these in conjunction, we can see three things. So, larger there is a larger shape change for more flexible rings, so for k theta equals 10, and also there is a larger shape change for the larger rings, and also marginally there is marginally more non-affine motion for the smaller rings compared to the larger rings. And most importantly, we see that more shape change leads to less non-affine motion, and less shape change leads to more non-affine motion. So, now finally we can look at the variation in the extent of contact between the rings, and we look at this quantity q tilde, which is this. So, this delta nij is the change of neighboring monomers between two rings, and we take mod of delta nij and sum over all neighbors and an average over all particles, and this q tilde is so since we have a finite temperature, this q tilde is non-zero even in the unsheared case. So, we take delta q tilde, which is q tilde minus q tilde at gamma 0 equals 0, and we see for both the flexible and the rigid cases, there is as we expect, there is an increase in this delta q with gamma 0, but the increase is less for the more flexible rings. So, which kind of means that the more flexible rings are stickier, and we see so this increase happens for both in the both below the threshold and above the threshold. So, both in the elastic and plastic regime, and in the elastic regime this is due to this kind of sliding motion, which is shown in the middle panel. So, sliding motion as well as rolling motion, and also there is some caged motion happening. So, the two particles move apart at short, move apart short distances, and then perhaps they come back again. I mean, there is no rearrangement happening there. So those kind of events happen, and also this rolling and sliding motion. And in the plastic regime, we have these as well as now rearrangements or T1 events which are happening. So we see that, yeah, just a second. So there is an emergent friction in the system. So we have the sliding and rolling motion. So obviously there is a friction, and so and with that, so I'll just leave the summary here, and you can read as I play the movie. So the top is the unyielded case, and the bottom is the yielded case. Both are for the more flexible rings, k theta equals 10. Okay, and with that, I'd like to end my talk. Not before I thank all the collaborators and the IMSC High Performance Computing Facility. That's it. Thank you for listening.
Just one quick question.
So is the asphericity because now there's a direction, right? There's a shear direction. Is there any correlation between how what's the major axis of these kind of ellipsoids with the shear axis, or is it just?
Is there any aligning happening?
Yeah, like do they align, or this just random?
So we have not like checked very deeply. So in this, I think over this tree. So in this previous work, we see in the glassy regime for or near the glassy regime for high values of k theta. So in this case, this high values of k theta means more aspherical shape. So there we see kind of this nematic order.
Okay.
However, I don't know if this adding this shear to the system whether it will align them or not. Perhaps we need to explore.
Wouldn't you expect them to? Now you have a field, so it should align along that. Yeah.
So I wanted to ask about the Q tilde that you showed at the last. So I was wondering if that gives some information about like the average number of neighbors it has or something like that. Does it provide any information about that?
So it's you mean the average number of rings, neighboring rings? Or,
yeah.
So this is at the like monomer level. So this delta, this delta Nij is the change in the neighboring monomers. So I mean this doesn't directly give a measure of like how many rings are nearby.
Okay.
Yeah.
Thank you.
No, I just had a quick question.
Yeah.
So in the model, you don't have the area constant, right? And so therefore you need k theta to make it make the model stable. If you set k theta to 0, do you expect it to still work, like the yield stays or something, or you need a critical value of k theta?
If we set it to 0, then I guess it will completely
collapse.
Yeah.
So you need a critical value, or is it just like continuously sort of increases?
So I don't know if there is a critical value, but this asphericity kind of depends non-monotonically on the k theta. So at very low k theta, you see the rings are like coiled, and they have a spherical shape more or less. And then if you increase k theta, becomes more aspherical, and then again if you increase further, then it becomes spherical.